apologies in advance. If I lose your places, I will try to stick to the important bits. But I think it's important, and I would like to motivate it for you, even though I think most people in this conference are going to agree with what I'm going to say. And that's, there's a lot of appeal in trying to mix and match quantum computing with machine learning, right? We kind of all agree on that. I don't have to preach to the choir. But it's not a bad idea to remind ourselves maybe why we think this is the case. Sometimes we have very nice arguments. Like, for instance, in the case of quantum enhanced machine learning, so this is the domain where we try to find quantum algorithms which help us solve machine learning problems faster. They're like two very common reasons why people tend to believe that it's a good idea to do it. And they're completely different, and they actually apply to different types of quantum machine learning, quantum enhanced machine learning. One has to do with an algorithmic appeal, right? So it's essentially, since the seminal work of Hasidim, Harrow, and Lloyd on quantum linear system solving, which sort of gave us a sniff of an exponential improvement in a very fundamental computation, there was this hope that we're going to find places we can apply this thing which we call quantum linear algebra, and I'll say something about it in a second. And machine learning seemed to be the thing that we want to do. This quantum machine learning has many constraints. Sorry, quantum linear algebra has many constraints, but they somehow seem to hurt less in a machine learning context. And the other part of the appeal has nothing to do with algorithms. It has to do with NISQ, with near-term quantum computers, which are, as you know, they have few qubits and they're shallow, constrained, they're noisy. They natively come with real valued parameters, not something you typically encounter in standard algorithmics. So it's not surprising that it's hard to find algorithms that you can run on such a device. And somehow, if you think of a quantum neural network type thing, or variational circuit, this kind of goes away, right? You don't have to worry about designing algorithms, right? It's the answers that you use, you optimize over it, and it does it for you. So it's quite appealing to somehow circumvent the problem of programming these small devices. Now I want to talk for a second about what I mean by quantum linear algebraic flavor of algorithms. So the idea is there to really interpret quantum mechanics in a very literal sense as linear algebra, right? So the quantum state is an n-dimensional vector of complex numbers, bearing the normalization, and density matrices and unitaries and Hamiltonians are all really large matrices, very, very large, as we all know, exponentially large, sort of in the number of qubits that we need to embody them. If you want to compute, inner products between large vectors, voila, you can measure stuff, and that's what it does it, or you can do swap tests. So down the line, as long as your data is encoded in these amplitudes, and as long as at that very moment, you kind of work naturally in a logarithmically smaller space, right? Because you have logarithmically fewer qubits. And now if you do standard quantum computing, which is polynomial in the number of qubits, somehow everything you do is confined to be polylogarithmic in the size of the data. So there's this feeling that, wow, whatever we do here is somehow guaranteed to be exponentially better than what you would do normally, where the problem size is the size of the entire matrix. So there's this hope that this is going to be a fountain of various algorithms with exponential speedups, right? There are, of course, many constraints, like condition numbers, how to prepare these states, etc. But it also was shown to work very well when the data comes preloaded, so to speak, in some sort of a quantum database. And when the data matrices, or whether the data lives in a low-dimensional linear manifold, which is very often the case. And we have quantum support vector machines, quantum k-means, etc., many, many wonderful algorithms, which did exponentially better than what we had at that point, right? The thing is, you can push it further, right? Probability distributions and stochastic operations also have exponential large encodings, right? So it turns out that all this works too well, right? When my data matrices are low rank, and when I can sample from vectors where the probabilities are dictated by the size of the entries. So you can have, n spins, but it still has 2 to the n probabilities assigned to the all possible configurations. It turns out that you can do most of these computations classically, right? So this is a sort of first done by the work of Tang and then others as well. We've achieved exponential speedups in essentially all the cases where we had exponential speedups in the quantum case. And some call this dequantization, right, of the algorithms. It is not really dequantization. We have not really touched the quantum algorithm itself, but we were inspired by it for sure. And when I say me, I'm really stealing the mantle of other people who've done the work, but we as the community. So I think it's a very natural question of, like, is it the case that everything this is somehow this quantum linear algebra flavored and quantum machine learning, is it all dequantizable? Because if it is, then at least we can forget about these really serious separations, which would be unfortunate. So we try to answer this question for the topic, for the problem of topological data analysis, and I will spend most of the talk today actually telling you what this is all about. And then in the end, I'll actually tell you our main result, which is not conclusively showing yes or no, but is providing strong evidence that some of this stuff should actually survive no matter how clever classical computer people are. And maybe I'll tell you a little bit later about the other aspect of the story is whether these algorithms are suitable for near-term quantum computers, because there were these two things that we liked about quantum-enhanced machine learning. So first of all, in the case you're not familiar with topological data analysis, and I will assume you're not, I want to put you in the right mindset to explain it. So it's a one-question Q&A. Like, what kind of machine learning is it? Is it supervised? Is it unsupervised? What is it? And the answer is you should think more like principal component analysis rather than neural nets. So it's about clouds of points. It's data points, many data points living in some large ambient space, dimension of which I don't really care about, and I want to extract features from it. This is something you can also do with principal component analysis. Like, principal component analysis is going to identify the principal components, and you can measure their magnitudes. These are going to be the singular vectors of your data matrix, and they will say something about the global shape of your cloud, right? And this is what you can extract, is this singular various sigma sub 1 up to whatever dimensionality you have, which is non-trivial. And PCA so sees shape, and it doesn't care about rotations, translations, rescaling. It's robust under this type of stuff. So it's all nice when things are linear. But what about when your data bends? You know, a fish, when it swims, it bends, but it's still a fish. I would like to have something which is robust to that as well. So topological data analysis tries to extract these topological properties from point clouds. So we're going to have an object down the line, which is in some larger space, and this object can have zero-dimensional holes, which is simply the number of connected components, one-dimensional holes, which are two holes in a donut, things which are like a circle and you cannot contract it further, two holes which are voids, like in a sphere, and we're going to count these things. And this is going to be the data we extract out of a point cloud. So the overall pipeline of TDA goes as follows. We have a point cloud where I have n points, and n is the quantity I will care about, not the inherent dimensionality, not directly anyway. And from this point cloud, we'll construct some kind of a continuous object. Think of it as a mesh, like if you're doing 3D rendering for the time being. But what we really do is construct something which is called a simplicial complex. I will tell you in a second what it is. And from this object, then we want to extract the number of holes, 0 holes, 1 holes, 3 holes, etc., up to k. And the number of holes of this object is what is called Betti numbers. So we're going to be talking about the kth Betti number. And my own face is in front of this. So this is sort of one block in a TDA, and typically you do this at various ways of defining this mesh, which kind of depends on your coarse graining. Like, when do you consider 2 points connected? How close do they have to be? And as you change this measure, certain features might disappear or reappear, and things that don't disappear are called persistent features. And you kind of want to analyze this. But for me and for the quantum computing community, we kind of want to focus on really this part of the story here, just going from the mesh to the Betti numbers. So as I mentioned, in fact, it's not really a mesh I care about. It's something which is called the simplicial complex, which is a catalog of all k clicks. Recall, a k click is a k-sized complete subgraph of my mesh, of my graph. And I want to have a list of all of them for every k. These clicks somehow tell me how the holes are defined. And to give you an example, here's a tetrahedron. Right here, it's these 4 points. And I have 1, 2, 3, 4, 3 clicks, so 4 triangles, which can be connected, but I might have no 4 clicks. So all 4 do not appear in the graph, in which case this would be a void. It has a hole inside. But if the 4 click does appear in my list, then it's not a void. Then it's a solid object. And smart people, including Hodge and Ekman, using a quite heavy mathematical machinery have shown that you can count holes in a linear algebraic way. So specifically, the kth Betti number for a given graph or a given mesh can be computed by finding the dimension of the kernel of the 0 eigenvalue subspace of a so-called kth combinatorial Laplacian. So this is a matrix associated to my graph, and it has this parameter k, which tells me how big a hole am I looking for: 0 hole, 1 hole, 2 hole, etc. And you can think of this combinatorial Laplacian as a sort of a adjacency matrix, but on the cliques. It's telling me when the cliques are connected and when they're not. And down the line, all we have to do is compute the nullities, so the dimensionality of the 0 subspace, of the zero eigenvalue subspace of these matrices. So to give you a flavor of what these Laplacians look like, so for the kth combinatorial Laplacian, its rows and columns are going to be enumerated by the k+1 cliques which appear in my graph. So I have n vertices. I have certain number of k+1 complete subgraphs. This varies from graph to graph, but each one of them is going to denote one of the columns and one of the rows. And the off-diagonal elements are going to tell me when two cliques are connected. And two cliques are connected if they share a clique of one dimension smaller, but are not a part of a larger clique. And diagonal numbers count something else. But I don't really want to care about the details for the moment. This is just to give you a flavor. What I want to care about is that the size of this matrix is somehow combinatorial, right? Because I can have n choose k+1 subsets of size k. So in principle, this is the upper bound on number of cliques. And this kind of tells me what I can expect the size of this matrix to be. It can be much smaller, but it can be this size. And when k, the Betti number that I care about, scares with n, this becomes super polynomial. And what I now have is a situation that I have a small object of size n defining a combinatorial larger object in a very succinct way. And that's sort of what you'll want for exponential quantum speedups without any hassle. So maybe to highlight one thing, the situation is not low rank. These Laplacians are in fact quite high rank. The Betti numbers are not, very, very large necessarily. It is not big data. It's big computation, right? Because I'm not going from n to polylog n, like the data size, to something logarithmic in it. I'm going from a computation which can be exponential to something which is polynomial. So that's sort of a good sign against dequantization. So let me summarize the story so far, abstracting a little bit from the math and everything that's unnecessary. So I give you, a cloud of data points, and I give you an epsilon, which tells me when points are connected. This gives me a graph. From this graph, I can, in principle, compute the catalog of cliques. And once I have a catalog of cliques, from this I can compute a combinatorial Laplacian, which is some large matrix, right, specific to each dimensionality of whole I care about. And I need to compute these Betti numbers. And this I will sort of refer to as the topological data analysis problem. So specifically, I will be caring about computing the normalized nullity, which is not the actual Betti number, but is the fraction of the Betti number and the maximal possible Betti number. That's the fraction of the number of eigenvalues which are 0 versus the dimension of the entire matrix. I will tell you in a second why I have to consider just this normalized quantity rather than the absolute quantity. And the idea of how to do it is to use quantum linear algebra type routines to estimate the nullity. And this brings about the algorithm of Lloyd, Garneron, and Zanardi, which sort of does this in a very elegant way, and we're going to discuss this now. So first of all, let's point out that counting eigenvalues, approximating the number of eigenvalues of a large Hermitian matrix in a quantum context is not that difficult. So provided that I can implement the Hamiltonian simulation protocol on my matrix H, which I can in many conditions, then I can do it as follows. So I take my large matrix H. It has spectral decomposition as shown. So it's some lambda I, and I will choose a random eigenvector, right? So I prepare my quantum computer in a random eigenvector of that. I do phase estimation of the time-evolved unitary of the Hamiltonian up to some precision gamma, which has to do with the eigenvalue gap, and I measure the eigenvalue. And if I see 0, I increase the counter. If I don't see 0, I don't increase the counter and do this polynomially many times. And what I'm doing with this is I'm counting the frequency of zeros. And this is the normalized nullity in the limit, and I'm approaching it in a very controlled way by the central limit theorem. To just mention this precision has to do with the fact that I kind of have to distinguish the smallest eigenvalue from the smallest in absolute value eigenvalue from the 0, right? You kind of want to do that if you really want to count the zeros. Now, you might know that I'm assuming that I can prepare an eigenset of H. In general, I cannot do that. But that actually doesn't matter. I can completely circumvent this problem in the following way. I realize that if I'm preparing a random eigenstate, well, this is just a resolution of the identity, right? In fact, this is the maximally mixed state. And then I can choose any basis as the resolution identity. So in particular, step number 1 says prepare any state, like any computational basis state uniformly at random. This will do, and do the algorithm as follows. So this is all very nice and very elegant and very simple. And I might almost say, okay, this is it, right? So if you want to do topological data analysis, then run quantum linear algebra for estimating nullity on the combinatorial Laplacian. End of story, right? The thing is, the story is a little bit more complicated than that. I will not have time to go into all the details. I'll flash it for you, then I'll step back and just tell you what you need to know for the rest of the talk. So one problem is that combinatorial Laplacians are per se not sparse. And as far as we know, we cannot represent them efficiently as a sum of local Hamiltonians, which means that I cannot really do Hamiltonian simulation on that efficiently. But what I can do Hamiltonian simulation on is something which is called boundary maps. And boundary maps are a different mathematical object using which I can construct combinatorial Laplacians. And in fact, I will be doing Hamiltonian simulation on this object which has to do with boundary maps, which is sparse, which I can simulate efficiently, and whose sort of kernel dimension matches the one that I really care about, of the combinatorial Laplacian. Second problem has to do with the fact that this construction somehow, you might recall that I said that the combinatorial Laplacian rows and columns are enumerated by the cliques, right? So in principle, obviously I need to know the number of the cliques. Not just that, I need to know which one is which. The catch there is that, you know, listing and finding whether cliques exist large enough, this is actually at least NP hard. So finding the largest clique is an NP hard problem. So in principle, this is difficult. So I need to have some mechanism which allows me to somehow identify these cliques. And I don't want to go there too much, but I need one of two things. Either I need to have a situation in which I can produce a random K clique uniformly at random, some mechanism which does that efficiently, or I need to have access to a boundary map oracle for Hamiltonian simulation where this boundary map is specific to my graph. In practice, what Lloyd and Zanardi and Garnerone do, they assume that you can sample a random clique from the graph. And you can do that when the cliques are plentiful. You take a random subset of vertices, and maybe with polynomially small probability, but not less than that, it is an actual clique, then everything works out fine, which actually corresponds to large Bethe numbers. So it's the regime we're interested in. Okay, so now let's summarize. What does the algorithm that I just described actually do? So it approximates an estimate of normalized Bethe numbers for a given graph. Approximates, this is the fact that I cannot necessarily distinguish very small eigenvalues from zeros. I might make a mistake there. Maybe I don't know the gap of the combinatorial Laplacian. And the second thing is that I'm doing sampling. So I'm going to have an error on this. So it's a gamma epsilon approximation. And I know that I can make it work when this gap is 1 over poly, because then it's enough to take 1 over poly precision in my gamma. And when I can prepare random cliques of an appropriate size. I call this problem RCS, random clique sampling. And in this case, the complexity of the algorithm is something like poly n, which has to do with n is the number of points, which has to do with Hamiltonian simulation and the fact that I have to iterate it many times to sample. 1 over gamma, which has to do with the precision of how precisely I'm measuring my eigenvalues, and the fact that I have to prepare the random cliques, which is the RCS cost. In contrast, if you look at classical approaches for this, now mind you, I don't think anyone really seriously tried to construct randomized algorithms to do that, inspired by the algorithm of LGZ. But the best we could find in literature is not much better than doing exact diagonalization. So you get algorithms which are somehow n to the k, where k is the size, the Bethe number that you care about, the size of the cliques you're going to consider, and n is the number of the data points. So now again, if k is somehow scaling with n, then this is an exponential runtime, or rather super polynomial. Whereas in the quantum case, there is no direct dependence on the size of the Bethe number itself. So this is a place where you can have an exponential improvement of the classical strategy. Right, so now classical algorithms are slow, as I've just said. If you want to simulate the quantum algorithm that I described, that probably is slow as well. But we want to somehow prohibit somebody coming up with a very clever classical algorithm which does the same thing as the quantum algorithm, right? So we care about the problem being hard and not the algorithm being difficult to simulate, right? That's sort of what you need to do when you're proving the hardness of a problem. Forget about the algorithm. For instance, the LGZ algorithm, you know, in itself, if you look at it, what it allows you to do is, for instance, eigenvalue sampling. So I prepare not a maximally mixed state on input, but a given quantum state, and then I can sample eigenvalues of my Hamiltonian, and this is known to be BKP hard already, right? But Bethe numbers don't care about fixing the input state; it has to be a random thing, and they don't care about estimating eigenvalues. So it's somehow clearly an overkill for what we care about. So what we did, we constructed sort of list of problems, computational problems that we do or might care about, and then we try to somehow organize them, which one is how hard. So first of all, finding exact Betty numbers, depending on how you actually define them and what settings you're looking at, there tend to be like NP hard or PP hard or Sharpie hard or P space complete even, depending on how badly you want to do it. The normalized Betty number estimation problem, where I want to really, sample from the zero eigenspace or not with uniform probability, and then I measure the frequency. This has not really been investigated, so the hardness of it is not clear. Approximate normalized Betty number estimation. So this is where I have a cutoff when I'm saying I'm counting eigenvalues below some number, but I'm not guaranteed that this is capturing just the zeros. This is the algorithm this is a problem that we'll care about the most. This is called A, B, and E, approximate Betty number estimation. And on the other hand, we wanted to extract sort of the real computational part, the really specific part of the LGZ algorithm specific for Betty number estimation, which is something we call the low eigenvalue density estimation. So here the task is I give you access to a Hamiltonian that you can simulate, and I ask you to estimate the frequency of eigenvalues which are below some polynomially small threshold. This is sort of what LGZ does.
Sorry, there is a question that may be relevant by
Sure.
Yeah, sorry, this is a few slides back, not a big deal, but you mentioned that the boundary map was sparse, but the Laplacian wasn't. And I was just confused about that because I thought the Laplacian was basically the square of the boundary map, like the boundary map times its dagger. Am I?
Yeah, but why would it then be sparse?
So doesn't that mean the sparsity of the Laplacian is just the square?
Oh, yeah, you're right. It cannot be more than that. Yes, you're absolutely right. You are correct and I'm incorrect. You're absolutely right. Yes, the sparsity.
It's not a big deal. I mean, maybe they're both sparse, and then you can just.
You're right. You're right, and in principle, one could simulate in that. The catch is in some, yeah. Yes, you're right. In principle, it could work with both. You can construct both, but this ends up to be a little bit more efficient. Yeah. But it will not matter for what I will want to discuss. But thank you for this correction. You're absolutely right. So for those who missed it, I stated that the combinatorial Laplacians are not sparse. In fact, they are, but it just so happens that it's easier to work with a boundary map, which is also sparse. Right. So yeah. So I wanted to now tell you something which is sort of obvious about the relationship between these problems that are defined here, which are all to do with combinatorial Laplacians and estimating their nullities, and what LGZ does, which has to do with estimating nullities of essentially an arbitrary Hamiltonian they can plug in. So one thing you can somehow show that, estimating these Betty numbers, when you really count the zeros versus counting everything below a threshold which is not more than polynomially small, not less than polynomially small, well, these are sort of equally difficult when you promise that the gap of your Laplacian is polynomially small and not less than that. The arrow means that it's a standard reduction arrow, means that if I can solve A, B, and E, then I can solve B and E in this particular case. Another thing which is kind of clear is that, if I can solve LLED and I can really implement the Hamiltonian simulation for the combinatorial Laplacian or the boundary maps, then I can also solve this A, B, and E using LLED. So this is somehow by construction. We designed it that way. But the difference is that LLED doesn't really care about the fact that I'm thinking about the combinatorial Laplacian. Any matrix that I can efficiently simulate will do. So this is something which is obvious. We don't have to think about this too much. So let me be a little bit more precise, but not infinitely precise. What I mean by LLED, so an input is a Hamiltonian or a Hermitian matrix, somehow given in a way that I can simulate efficiently, either via an oracle, sparse oracle, or as a sum of local terms, whatever. And you're given a threshold, which is promised not to be less than polynomially small in the number of qubits. And the task is to approximately estimate the ratio of the number of eigenvalues which are below the threshold in absolute value versus dimension of the entire system. There's a little delta here because, since I'm doing down the line, I'm going to be doing phase estimation, I can make a mistake, right? If something is really close to my eigenvalue, I can still count it. So I'm going to put a little delta buffer there to say I don't care about it. When I'm promised, when the gap is promised, then this is not a problem. Then I can always go below the gap and everything turns out to be fine. So this is my problem. And just to remind you that this approximate Betty number estimation is solvable by LLED when I can simulate the Laplacians. And LLED is solvable by approximate number estimation when the Hamiltonian is specifically a combinatorial Laplacian or an encoding of one. I don't want to go too much into detail about what I mean by that. But they're kind of related. But to be honest with you, of course, this problem LLED is not the same as topological data analysis. In some sense, it's a little bit more general. In some sense, it's more general because it doesn't really care about the particular matrix. In some sense, it's more restrictive because I cannot really do them for all combinatorial Laplacians. But it's the closest thing which we could actually tightly characterize. And this is the characterization, the main result, that this problem, LLED, is DQC hard when things are formalized in an appropriate way. So this is DQC1 for perhaps you have not encountered this. This is a computational class defined for the so-called one clean qubit model. So it's a model, it's very similar to the standard BQP model in which you have an input register, and then you apply a bunch of gates and you measure one qubit, and what comes out is sort of the output of your computation. You can use it for decision problems. But the catch here is that I'm only allowing one qubit to be in the pure state 0, and everything else has to be in a maximum mixed state. So this really changes the computational class. It's a weaker model. You can clearly simulate it in BQP, but it's still widely believed that it's not simulatable by classical computers in polynomial time. And I personally don't have that much intuition why this is the case, but I mean, people like Shore and maybe Aram knows a lot more why these things are necessarily hard, but it seems that people have really tried to estimate traces of unitaries specified by circuits and failed very hard. There are some topological reasons why it should be hard, but let's believe them, that this is not going to fall as easily as maybe quantum machine learning did by sampling algorithms. So this is going to be my hardness statement. It's as hard as DQC1. Now, I'll tell you just a little bit about how the proof goes, because it's actually very easy once you set the problem such that we can solve it, because Fernando Brandao essentially did all the work for us. So Brandao showed a while back, so I forgot the tilde on the A in the second line. He showed that given access to a Hamiltonian, estimating the sum of eigenvalues below a threshold, normalized sum of eigenvalues below some threshold, is DQC1 hard. So to explain, this is different from the question we're asking, is because we don't want to sum them up, we want to count them, right? So if instead of having a eigenvalue lambda, I had 1, but I had the number of ones as the number of non-zero eigenvalues, this will be the same problem, but it's not, right? So Brandao says that computing the mean of the distribution of eigenvalues in this tail of the spectrum of the Hamiltonian is hard. What we're saying is that using the LLED procedure, we can construct a histogram of this distribution. So let me show you what I mean by this in a figure. So if this is
sorry, it's been 30 minutes, so there's 10 more for discussion.
Okay. So
yeah.
I'm gonna be done in 3. Okay, I'm not gonna bother you. The main point is that I want to recover the mean of a distribution, but what I can really construct is a histogram, because each one of the boxes of a histogram is a difference of 2 outcomes of 2 different LLED runs. So this is a non-adaptive reduction from one DQC1 hard problem to our LLED problem, so they're somehow equally hard for many intents and purposes. So it's an easy solution once you realize what you want to do, and when you just have to get your epsilons and deltas. So this is sort of the final result. It's a little bit of a handful. So the main thing is here, like that the LLED is DQC1 hard, and in fact, when the Hamiltonians are log local, I'm sorry, this should be up, then they're equivalent. So you can also solve DQC1 using LLED because the reduction was to a DQC1 hard problem. And all these other relationships are somehow relatively easy to infer. And what is sort of the interesting thing is to think about beyond just topological data analysis and what kind of algorithms can lie in these things. And it's interesting because they also all somehow have something which seems to be quite hard in it. So I'm going to tell you about this in, well, like 1 minute, because we thought about it. So on the left-hand side in red, I have problems which are all about the combinatorial Laplacian. On the right-hand side, I have problems which are all about counting nullities or counting particular parts of the spectrum. And we thought about problems which lie in both regimes, which are somehow easy to get to from the works of Lloyd et al. So for the combinatorial Laplacians, stuff which has to do with combinatorial Laplacians, but it's not eigenvalue counting, is, for instance, complex network analysis, where it turns out that computing certain spectral entropies, specifically Rene entropies, is an interesting thing to do. And in certain cases, this could be DQC1 hard. Of course, we cannot state that because the hardness are for arbitrary Hamiltonians, which are simulatable, and in our case, we have combinatorial Laplacians. So this kind of motivates, let's kind of figure out if combinatorial Laplacians are expressive enough to keep the hardness or not, which we don't know. On the other hand, playing with just estimating zeros, well, it's kind of cool because estimating nullities is sort of the same as estimating the rank. And estimating ranks of large sparse matrices is something people care about. I don't really have a killer app for you at the moment, or working on it. But sort of if it should happen that this matrix can be something like a dataset matrix, something relevant, something very expressive, then we get the DQC1 hardness sort of immediately out in this type of a domain. Last slide that I want to spend any time on is about, we thought about, how difficult is it to run these things from a NIST perspective. And as you all know, there are at least 4 things that we care about for a killer app, which has to do with, the size. Turns out 200 perfect qubits would be enough to beat the best classical algorithms. With respect to tolerance to noise, it's pretty much unclear. Just in terms of the right measures, there is a bit of robustness in the gap, right? If my problem is gapped enough, then if my eigenvalues are the only thing that gets really perturbed in the end, then I can tolerate a little bit of noise, but this is certainly not something that NIST people would be happy with. With respect to architectural limitations, that's unclear, but whomever figures out how to implement Hamiltonian simulation for chemistry very efficiently, which people are really trying to do, this is applicable to our case as well. And people seem to believe that topological data analysis is an interesting thing. Maybe I can tell you about that if somebody has questions, but I honestly am not really the expert. And with this, I will end. So we kind of try to answer the question of whether the thing that the algorithm of Lloyd et al. For topological data analysis does is hard. It's not entirely clear, but there are spin-offs which might be interesting, but their application thereof is not as clear. Yeah, but it is likely that this will not be dequanted, certainly not by the techniques proposed by Tang and collaborators, to our understanding. And I would like to thank Chris Cade and Casper Jurek for this work, and our funders, Quantum Software Consortium. And with this, I will end.
All right.
Time for questions, I suppose, if any.
Yes, there's 5 minutes for questions, so thank you very much. And now we can take questions. I guess maybe I can start with a simple one that you already hinted at, like where are these topological data analysis relevant, right? There's a simple...
Yeah, I wanted to title the slide. I knew you were going to ask that, but I felt this was too cheeky. So I have to tell you, I'm not an expert, so I looked it up, right? So here's what we managed to find. Right? In terms of topics of application, people have applied it to pretty much a lot of things, from spreading of, analyzing the spread of epidemics, analyzing organization of the brain, etc. You can find a bunch of references here if you're interested. I would like to highlight one application which was done by our quantum machine learning colleagues, by Alessandra Piero and Menigioni, which is about characterizing multi-party entanglement, which is kind of an interesting thing. It is not very conclusive, but it's an interesting thing to do, to simply see if topological data analysis tells us something. Now, from a beyond application, just how it's applied, from this very nice review paper, 1710, that maybe you're seeing my mouse that I'm pointing to, that I read like yesterday. It seems that there works with topological properties that directly what you care about. For instance, when you're studying nanopore structures in chemistry, there's a paper which shows that the data is really capturing the thing that you're trying to analyze in the material. So it's a rather direct application. But most of the time, what people do is use it as a feature extraction method. So it extracts features from data. You generate these persistent diagrams, which come from using many different epsilons, the mesh resolution, so to say. You do topological data analysis on top of all these things, and then you analyze the persistent diagrams themselves. It's like a, I'm not going to say dimensionality reduction technique, but it's going into that direction. People have done it quite a lot. So I know that I've read articles saying that this is sort of, for some people, the next big thing, but it's kind of clear that the math is hard. It's difficult to apply because of it. It is not as well connected to standard linear algebraic techniques in machine learning. And it's computationally difficult, right? So it's hard to somehow provide conclusive evidence that it's really extremely useful, as maybe it is for some other techniques. That's as far as I know.
Okay, thanks. I'll take a look at these references.
Yeah,
and there's a question from Florian. You can go ahead.
So in the beginning, you emphasized that for many of these techniques, it's a kind of bottleneck to get the data into your quantum device. So I missed a little bit. How is that? How is
right.
that done? Yeah.
Right. So
is that a bottleneck?
Yeah, no, because the data is small. So I'm happy with the runtimes which are proportional to the number of my data points, right?
So can you repeat the question?
Yes, of course.
Vedran,
So maybe Florian, maybe yell if I got you wrong. The question was in many of these linear algebraic quantum machine learning algorithms, the problem is that you somehow have to get exponential amounts of data into the amplitudes of a quantum state, right? And if you want to count that as a part of the computation, this costs as much. It costs n, and you're trying to do things polylogarithmically in n, so it kind of kills all benefits. You want to do it as a pre-processing step. In this topological data analysis algorithm, the catch is that the algorithm is actually exponentially slow if you do it classically. So my data is n, that's fine. N is fine. What is not fine is exp(n). So the preparation, which costs as the number of points, is something that I can live with, and I can somehow explicitly construct unitaries, explicitly construct the Hamiltonians that I want to simulate in this case, and this is not taking me outside of the cost that I'm happy to live with. If this is maybe answering your question. Maybe if you want another way of looking at it, the space which is exponential dimensional where I analyze the data, which is the space of cliques and their connectivity in the combinatorial Laplacian space, I have an algorithm which generates it. Right, so somehow I have an algorithm which efficiently generates these high-dimensional data points, so to speak. That is the algorithm which tells me, the structure of the Laplacian from a few data points.
Thanks. There's one. There's a related question, I guess. Can you go ahead and ask the question yourself?
Me?
Yeah.
Yeah. So related to this question of applications, so when you're looking at the K homology, this the space of K cliques,
yeah,
what values of K do you think are the ones that would typically be used?
Yeah, that's a really fair question, because if I care about low Ks, then there's no problem. Everything's polynomial anyway. The fully honest question is I have no clue. To defend the entire approach, I suspect that not much has been done, right, with high Ks, right, because you cannot really compute it. Now,
but it could be that people haven't even tried because it's too hard.
Right, it might be. So I suspect that somebody thought about, whether your embedding space has to be large, at least as large as K to be able to consider this, or maybe exponential in K to make sense to consider these K-dimensional voids, etc. I don't know. That's the long story short. I honestly don't know. From what I gather from these review articles, there's no explicit mention that nobody cares about high Ks. Nobody says we only care. It's just the fact that they analyze it up to some K and then they stop.
All right.